Well, we're almost ready to transition to our next significant topic of study. And to help with that transition, I'm going to show you another example involving this fundamental theorem of line integrals. So the fundamental theorem of line integrals involves vector fields being conservative. And there's a given path, r of t. So let's suppose I have a problem and that I have been told that the vector field is indeed conservative. And that the particular path I'm looking at is a closed loop or path. So for physics people, we're going to want this to be in the counter clockwise order. But for the not physics people, let me just give you sort of a visual what's going on here. So let's suppose that we have, let's say, in 2 dimensions, a path that goes from here to here, and then it goes up from here to here, and then it curves back down, but it takes us to the starting point. This is the opposite direction of our standard clock. The clock goes this way. This is opposite of the clock. Or how about a simpler example? How about just a circle going the opposite direction of the clock? Or maybe something from the world of polar, a cardioid that goes this way, opposite the clock. So each of these would represent a closed loop. This one is actually the messiest one because it would take 3 separate r functions to write it out. So the assumption is that the path completely closes itself in. Okay, so for you science people, think circuits. Something completely closed off, like a circuit. All right, so I'm going to just rewrite this and think circuit, C-I-R-C-U-I-T in the English language. Circuit. And for the physics people, this would be more meaningful. But for you people that are just cranking out math because your teacher's making you crank out math, I want you to see something. Let's suppose that we pick one of these paths. Let's take this one because we've never actually played with the function that looks like this before. And so let's suppose that its starting point is actually the point 2, 8. That's this point right here. All right. So the way this goes is I would have to give you some algebra to represent this, or maybe I don't, because I don't actually need to use this to integrate if I use the fundamental theorem. What we need is the potential function f of x, y. We would need that potential function f of x, y. And I'm going to show you for this problem, you don't even need the algebra for that. We know that the gradient of f would be the vector field because that is what a conservative vector field is. The conservative vector field, the gradient of the potential function is the vector field. And according to the fundamental theorem, if all of that is true, there's a shortcut to evaluate. Now, let me show you notation. If you have a closed loop, this notation goes in the line integral. This little circle symbol represents a closed loop that is counterclockwise. Some textbooks use this as a shorthand so you don't have to sit there wondering what's the curve or path look like. They're saying, nope, it's a closed loop or a circuit. The fundamental theorem says, since this is a conservative vector field, all you need is the potential function. And then we're going to evaluate it from the starting point to the ending point. Well, wait a second. The ending point is the starting point. And we should hopefully remember from Calc 1, if you start and end at the same place, the net result of this is going to be 0. And notice what I'm saying, the net result will be 0. Think of an electricity case. It might gain some charge and then lose some charge. The net change will be 0 at the end. The net change will be 0 at the end if the vector field is conservative. If the vector field is not conservative, then that is what the next section of the book is going to be about. What happens if that's the case? So, my students, summary. If F is conservative and R is a closed loop or path, those two are enough to justify that the work will be 0. That the work done will be 0. If you can show the vector field is conservative, that's on you to do, and this closed loop path is provided, then you can say the work is 0. And if you want to use the fancy new notation, you could dress it up, put a nice little belt on it. It'll be great. Next time, we'll start to look at what if you have a closed loop or a circuit and it's not conservative. That is a pretty big topic also.